So we're happy to have Jonathan Leake from Waterloo. Will tell us about capacity.
Yep. So thanks for having me. And so yeah, let's get started. So this is the name of the talk, or at least the first part of the name of the talk. Before I get going, I just want to tell you kind of the upshot of this method. So the point is that you often have some desirable quantities, some quantities you want to compute, maybe you want to approximate or bound, something you care about. And the general idea here is what we're going to do is we're going to encode those quantities as the coefficients of some polynomial with nice properties. And then that polynomial is going to induce some kind of convex optimization problem. And we're going to try to, again, bound or approximate these quantities we care about that are often hard to compute using this convex optimization problem. So that's the overarching idea. And when I was originally kind of thinking about what to talk about, I was very overly ambitious, but now that has been reduced to something that should sit within the talk time. So what we're going to do is we're going to talk about two different approaches to approximating the permanent. That's going to give us two kind of results that are then going to build up to the result we need to talk about improving the approximation factor for TSP. So that's the plan. Okay, so let me first write for you the problem associated to the permanent that maybe many of you have seen. So suppose I give you a non-negative entry n by n matrix. I'm going to denote it that way from now on. Okay, what you want to do is you want to compute the permanent of this matrix, which is defined as follows. So you sum over all permutations, and then you take product of the entries corresponding to that permutation. Okay, and there is a classic joke about the permanent that I heard from Barvinok, but I can't guarantee he was the one that wrote it, that the permanent is like the determinant, just only simpler, right? And it's simpler because there isn't this weird -1 to the sign thing, okay? But this is a joke because this thing is sharp P hard to compute. Okay, and even if the matrix just has 0, 1 entries, it's already hard to compute because that is the same as counting the number of perfect matchings of a bipartite graph. Okay, so instead of trying to compute this, then we try to approximate it. There have been a number of algorithms that approximate. There's a lot of work done on this. The first algorithms that I know about that solve the 0, 1 case is this randomized 1 plus epsilon approximation from Gurvits and Sinclair. That was later generalized to any matrix, non-negative entry matrix, by Gurvits, Sinclair, and Vigoda. So the first one was 89. The next one was 2001. And then there are a number of deterministic approximation algorithms, but maybe you don't get as great of an approximation. You only get a simply exponential approximation. Okay, and I'm going to talk about two of those approaches today. One of them is due to Lineal, Samardnitsky, and Victorson in '98, okay, via matrix scaling. And then another one is due to Gurvits in 2004, which is kind of the spawning, around the point of spawning of this notion of capacity that I'm going to talk about now. Okay, so here's Gurvits' approach to approximating the permanent. Okay, the idea is I have this matrix and I sort of come up with some polynomial based on the matrix, which is defined as follows. I take the product over all the rows of the matrix, and to each row, I come up with this linear form associated to the row of the matrix, and I take the product. Another way to write this would be the product over AXI, where X is a vector. Okay? And I want to make two comments about this polynomial. The first thing is I've given you a very nice formula for it. Okay, so it's easy to evaluate. And the way it connects to the permanent is that actually a particular coefficient of this polynomial is the permanent of, M. So the perimeter mem is the coefficient of this monomial x1 times x2 dot 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 times xn, which I'm going to denote as follows from now on. So that'll mean like the all ones coefficient of the polynomial. Okay. And so we have this kind of interesting situation where we have a polynomial that has a very nice formula for evaluation, and yet one of the coefficients is very hard to compute. Okay. And so now I'm going to write the theorem of Gurvits that leads to this kind of convex optimization approximation algorithm. Okay. There's going to be some terms in the theorem that I haven't defined yet, which I will do that in a minute. Okay. So let's, yeah, I guess I'll just do it. Okay, so here's the theorem. This is Gurvits 04. Okay. So let P be some polynomial, non-negative coefficients in n variables. And suppose it's homogeneous with respect to with the degree equal to the number of variables. If this polynomial P is what's called real stable, which I haven't defined yet, then we have the following bounds on this coefficient that we care about. So here's another thing I haven't defined yet, but I'm about to. There's something called the capacity of P, upper bounds this coefficient, and also lower bounds it up to this factor n factorial over n to the n. Okay, and this thing that I've written, this capacity thing, is defined as follows. So you take the infimum over the strict positive orthant, and you evaluate the polynomial, and you divide by the product of the variables. Okay, I'm going to shorthand write this from now on like that. Okay, and so the idea here is if we can show that this polynomial has whatever property this is, and we can show that this is easy to compute or is some kind of convex optimization problem, then this is going to give us some simply exponential approximation to the permanent, because this is essentially, it's a little bit better than e to the minus n. So that's the general idea. Okay. So now we need to answer some questions though. First of all, what does this real stable mean? Okay, there's a lot to say here, but I'm going to try to give you some high points. Okay. So at the end of the day, what this sort of is a multivariate version of real rootedness. Okay, so if I have a univariate polynomial that has only real roots, then I get something called the Newton's inequalities. Which say something like it has log concave coefficients. Okay, and so you can imagine maybe if there was some kind of multivariate version of this, these log concave coefficient inequalities, this is saying some inequalities between the coefficients, would be able to translate somehow to these types of inequalities. Okay, and so let me say that a little more explicitly. The point of this class of polynomials is that it captures log concavity, and also another sort of nice property that's a little more related to distributions rather than polynomials, but something called negative dependence. Sort of a strong form of negative dependence. If you don't know what this means, that's fine. I'm not really going to use this. I just want to put that word out there because that is a word very closely related to these real stable polynomials. And later we will connect this more directly to distributions, and then maybe we can see that a little more. And the third thing I'm going to say about this is that this class is robust under some natural operations. Okay, in particular, if I take partial derivatives, if I take a partial derivative of a real stable polynomial, I get something real stable. If I plug in some variables to be equal to some real numbers, I get a real stable polynomial. Okay, and also if I do things like set a bunch of variables equal to the same variable, that also preserves real stability. Okay, and we're going to come back to these operations later. And there's a huge theory here actually about things that preserve these polynomials, but that's all I'm going to say. Okay, I'll also give you some examples which maybe can make the link a little bit more clear. So I'm going to give you two particular examples of some classes of polynomials that have this property that will be important for us. So one is spanning tree generating polynomials. Okay, so what do? I have a polynomial. All of its variables are indexed by the edges of some graph. And I sum over all the trees in that, the spanning trees in that graph. And I write x to the t, which what I mean by that is it's just the product of all the variables associated to edges in the given tree. Okay? You can also add a little bit of a kind of a positive factor here. So if this is always greater than 0, you can also add something like this. Okay? And there's another classic example. Which are things in the form you take a determinant, you sum over a bunch of variables times a bunch of PSD matrices. Okay? And in particular, if these matrices are diagonal, then this is a diagonal matrix of linear forms, non-negative coefficients. The determinant is just the product. So in this example lies this polynomial Pn. Okay? So we have a sense of real stability, and we have that our particular example here is real stable. So then what is this capacity? So the first thing to point out is that if you replace xi by e to the yi, and then you take log of everything, you end up getting a convex program over all of Rn. This is a convex program up to some particular transformation. And so this means that it's easy to compute, or at least approximate very well, since this Pn is easy to evaluate.
Is this the same, is this true for any real stable? Or just for?
No, sorry, I'm sorry. This is for anything with non-negative coefficients. Doesn't require real stability, actually. Real stability would give you something more like some kind of concavity without the, actually I'd have to think about it. Well, I'll say for now, for anything with non-negative coefficients, this is a convex program up to log x transformation. Okay. The other thing I'm going to say about this is if you have some extra features, we're going to be using this a little bit later, or digging into this more a little bit later. If you know that the polynomial evaluated at all ones is 1, so the sum of your coefficients is 1, and you know that the gradient of the polynomial at all ones is the all ones vector, then essentially what's going to happen is this is going to give you some very strong information about the gradient of this log x transformation of this. So you're going to be able to compute exactly what this infimum is, just using calculus. And in fact, it ends up being just 1. And again, that's also for anything with non-negative coefficients. And so in particular for our polynomial that we've been looking at here, these two conditions just mean that M is doubly stochastic. Okay? And if you haven't seen it, what that means is just the row sums are equal to 1, and the column sums are all equal to 1. And the way you can see how these relate, this thing says that this evaluation is 1, and actually this term is equal to the gradient. Okay, so if you have doubly stochastic, you get these two properties, and then you get this bound on the capacity. And so what does that say in that particular case? So now if I combine this theorem with this, it says that in this doubly stochastic case, you actually have more explicit bounds on the permanent. Okay, which is this van der Waerden lower bound for the permanent that was proven by Gurvits and Klein in the 80s originally. Okay, this was a conjecture from like the 30s, I want to say, proven in the 80s, and this is, I would say, the simplest proof that we have now, essentially running through this argument. Okay, and so the upshot of this first part of the talk is just that, right, I had some generating series, some generating polynomial that was easy to evaluate. And I had some particular coefficient that counted something, or I guess computed something here that I really cared about. And I could translate trying to compute that thing into actually just computing some convex optimization problem based on this polynomial that I could easily evaluate. Okay, there's a number of other problems where this sort of thing is used. I won't be able to talk about more than this. So Gurvits himself, along with just himself a few times, and then also along with Simonyi, proved similar bounds for the mixed discriminant, the mixed volume. You can also use this type of technique for lattice point counting or approximate lattice point counting. So you can write down some generating series for the lattice points of some class of polytopes. Those lattice points are hard to count, and yet the generating series is easy to evaluate. That's due to some papers of Hardigan. Gurvits also had a paper on that, and then a paper of myself with Peter Brendan and Igor Pak. And then there's also a number of things that you can do with sort of similar techniques where you're either counting or optimizing something to do with matroids. Maybe matroid intersection, maybe you're optimizing a function on the basis of a matroid, something like this. And there's a number of papers there. The first two papers in that direction are due to are Inari and Obeskaran, and also Strazek and Vishnoi. And then there's a number of kind of follow-up papers with Inari, Obeskaran, and Quiquilu and Cynthia and Zant. Okay. And there's probably some other things I'm missing there, but I just want to give you kind of a sense of the sort of things that this is used for.
What if M is not doubly stochastic?
If M is not doubly stochastic, well, we can't say much right now, but hopefully in the next part, I'll say maybe if M is close to doubly stochastic, we can say something.
You can scale it, right? If the percentage is non-zero.
Yeah, so this is sort of the next thing that we're going to talk about. So. Okay. So that leads us into the next approach to the permanent, this permanent approximation, which is via matrix scaling. There's a huge amount of literature and others and just thought around this problem. I'm not going to be able to talk about very much of it because I want to get to the TSP application, but at least one of the theorems along the way will be useful to go to that final application. So this was actually the original approach to this deterministic approximation, simply exponential approximation algorithm to the permanent. Okay, this was Lineal, Samorodnitsky, Vigorson in '98. This is before Gurvits. Okay. So here is the problem, this matrix scaling problem. or at least the specific one I'm going to talk about today. You take some non-negative entry matrix, n by n. You want to determine some diagonal positive definite matrices, R and C, so that RMC is doubly stochastic. Okay. This is a very specific version of this problem. You can also ask for other marginals, and there's a huge amount of generalizations of this, again, which I unfortunately won't be able to talk pretty much anything about. Okay, this problem even has a long history. I think it's originally studied maybe even earlier, but at least as far back as the 60s. But anyway, history I won't talk about pretty much at all. But I will talk about just how you can connect this to permanent approximation, how they did in this paper. Okay. The idea is that if you could find these R and C, then the permanent of this scaled matrix is just equal to the permanent of the original matrix times some determinants of these diagonal matrices. So it's really just the product of the diagonal entries of each of these matrices times the original permanent. Okay, this is just straightforward from the expression for the permanent. Okay, and we also know, right, if I could get this R and C exactly, I would have that this is doubly stochastic, and from this result that I just wrote down up there, we would know that this permanent is bounded like this. This is essentially simply exponential. And so now if you could get this R and C, you could approximate the permanent of this by, say, the number 1, and then you would just divide by the determinants of these matrices, and you would get an approximation with the permanent of L. Okay? And the way that this is done in this paper is using an old algorithm called the Sinkhorn scaling algorithm. Okay? And maybe many of you have seen this before, but the way it goes is as follows. It's kind of a naive algorithm. You say, okay, well, whatever I choose for R is scaling the row sums of M, and whatever I choose for C is scaling the column sums of M. So let me just pick the most natural R I can think of. I'll just pick it to be the inverse of the current row sums. Okay? So that'll just basically make the row sums equal to 1 if I now multiply this M by R. Okay, of course, the column sums are still wrong, so let's just do the same thing for the column sums. Okay, but when we do this to the column sums, we possibly mess up the row sums, so let's go back and try the row sums again, and we're just going to repeat this for some number of times. Okay? And this is a pretty naive algorithm. It's not clear why it should work or under what conditions it should work. Okay, but one of the results of this paper was to show that it does work pretty quickly. So if you start off with something that has positive permanent, this is equivalent to just checking whether or not a certain bipartite graph has a perfect matching. Counting is hard, but checking is easy. So if you have this, then you can basically get the right row sums and approximately the right column sums after polynomial many iterations. Okay? And so this algorithm sort of works for, I guess, approximate scaling after polynomially many iterations. But then this sort of leads to a problem with our original approach, because now we have the situation where if we knew that this exactly scaled it to be doubly stochastic, we could then just apply this argument and we would have an approximation with the permanent of M. But if we don't quite have that it's exactly doubly stochastic, then it's not clear exactly how we can use something like this, okay? And so this is going to lead to the second theorem that I want to state. So the theorem I'm going to state is much more recent than this result. It's due to Gurvits and myself in 2021, but it is very influenced by an analogous result for this specific permanent problem in this paper here. Okay, so I'm going to write it and kind of cite both of us. Okay. So it's going to start off similarly to the previous theorem I wrote down. Suppose I have an n-variant polynomial P, and it's homogeneous of the degree equal to the number of variables. If P is real stable, again, looking just about the same as what I had written down before. Okay, but now we're going to assume a few more things. So we're going to assume also that we have this all coefficients sum to 1 feature. And now we want to sort of translate this approximately doubly stochastic into something more polynomial. Okay, and if we saw what we saw before was that the column sums of the matrix were given by the gradient of this associated polynomial. So that is going to be the condition now we're going to assume. The sort of generalization of the column sums being close to all ones is that the gradient of this polynomial to all ones is close to all ones. Okay, so it has to be equal to some delta, which is bounded by 2. 2 is the best that you can do. If you have all this, then we have upper and lower bounds actually on this capacity part. Okay, and like I said, this strengthens a very similar bound, but specifically for the permanent case from this paper in '98.
So if delta is close to 1, this approaches half to the n?
That's correct.
And so you improve the e to half in the.
No. So if this would be the column sums. If the column sums are close to all ones, but with delta error. So if you would get close to all ones, this would be like very small in theory. After some polynomial number of iterations, you get that, right? This is, if you choose PM here, this would be the column sums.
Right.
So this would be close.
So for doubly stochastic, delta is 0.
That's correct.
So you can get arbitrarily close to the approximation factor for the permanent.
So no, it's just an approximation factor for capacity.
Oh,
So then this e to the minus n is still there, and you just want this to not be anything worse than that.
Okay.
So that's the idea.
For any real stable.
That's correct.
As opposed to.
Just the permanent in that particular situation. That's right. Okay, and so yeah, let me just write out explicitly what you get from this. If you combine the two previous results, if the row sums are 1, and the column sums are about 1, then what do you have? Well, the original bound was capacity bounds above the permanent, and here the capacity is bounded above by 1. So I can write this. And then before I had bounded below by n factorial over n to the n times the capacity, and then that can be bounded below further by this. Okay. And so, right, we're using this problem to try to approximate some quantity or bound some quantity. And sometimes maybe you want more than just a sort of convex program that can approximate something. You want to know something more explicit about the quantity you care about. And this is saying that this capacity term, right, whenever I have some very specific information about the gradient, I can say this is equal to 1. But as that information deteriorates, I still get something that's sort of a, I guess, simply exponential nature. And there is just a huge amount of literature on generalizing scaling. I'm going to talk about one particular paper, but there's a lot of papers I'm not going to be talking about. So sort of what happened in this algorithm and the way that they proved this theorem is they sort of used the permanent as a measure of progress for this algorithm. Okay, of course you can't compute it on the fly. That's the whole point of the algorithm, but they could show that in every iteration, the permanent had to increase by a certain factor. And that gave them in turn a bound on the number of iterations they need to kind of get this permanent quantity large enough. Okay. And it turns out that you can do a similar thing using this capacity as a measure of progress. And this in particular was used in one of these generalizations of scaling to what's called operator scaling, where instead of a matrix now you have some linear operator on matrix spaces. There's some analogous notion of scaling the operator to be doubly stochastic. Okay, this paper is Gurvits, and Vigderson in 18 or somewhere around there, and they analyze an algorithm of Gurvits from 2004 from a different paper, and yeah, this enables them to prove They solve some kind of non-commutative version of the polynomial identity testing problem. It's very interesting how it all connects. Like I said, unfortunately, I won't be able to talk much more about it, but there's been a huge amount of work after that, generalizing matrix scaling to different types, different sort of operator scaling and beyond, and also sort of generalizing what it means to scale, looking at different group actions. But that's all that I will say about that. Okay, so then before we head to the main application, what I want to do now, and I guess I'll do it maybe over here, I want to revisit this question of what exactly is capacity. Because I want to say a little bit more about it, and I want to connect it a little bit more to some of the objects that we're going to need for the TSP application. Okay, so now we're going to start with a probability distribution. I'm going to call it mu, and admittedly, I'm going to be doing things like p sub mu. Now the mu is mu and not an m. It'll kind of look like p sub m, but here we are. Okay, so let this be a probability distribution. On the subsets of 1 through n, or if you prefer, the vertices of the 0, 1 hypercube. Okay? And with this distribution, we're going to construct a certain generating polynomial. As follows: p mu of x1 through xn is going to be the sum over the subsets of 1 through n, the probability mass function of mu at the set S, and then times x to the s, which is just going to be the product of the variables indexed by entry elements of S. Okay, so this is somehow I'm taking the probability mass function of this mu and just making it the coefficients of this polynomial. Okay, And now what I'm going to do is I'm going to set up a sort of dictionary between real stability of this polynomial and some notion related to this distribution mu. Okay, so maybe the most obvious thing is that the coefficients of the polynomial are just the probabilities, how it was defined. Okay. The notion of real stable has an analogous name in this distribution world, which is called strongly Rayleigh. And this is exactly some sort of strong notion of negative dependence that I was referring to before. Okay, this is talked a lot about by Waerden and Leake in 2009. Paper all about these distributions and their properties. Okay, the gradient that we keep looking at all ones. So gradient of P at all ones. This is precisely the marginal probabilities of the distribution. Or if you prefer this hypercube thing, the hypercube interpretation, it's the expectation. Okay? There are a number of operations that I referred to near the beginning of the talk. There were things like taking partial derivative. There were things like setting maybe variables equal to 0, maybe setting variables equal to 1, and then this idea of setting a bunch of variables equal to the same thing. So those have interpretations on the probabilistic side. The first two are conditioning. You're either conditioning x1 I to be in your set or out of it. Okay, this plugging in 1 is going to sort of sum all the terms that had xi in it. So this is like marginalization. And this last one is probably the most hard one to sort of explain, or not explain, but sort of see what it's doing. It's just sort of counting. So basically, if I take a set S and I set all the variables associated to S to a single variable, then if I look at this new polynomial, if I have something like x to the third in a particular term, that's some probability that 3 elements from S came in my randomly chosen set. So this is some kind of getting at something like counting. So that's what I'll say. Okay. And the final one, which maybe will also more connect it to what we're about to talk about, is a more conceptual interpretation of what this is doing. So now if I change this all ones to some vector alpha, this is going to be minus log of this infimum. But now all that happens here is I put x to the alpha in the denominator instead of x to the all ones. This is equal to a certain entropy maximization problem. So this is the infimum over all nu, such that the marginals of nu are equal to alpha. Or if you prefer this, the hypercube interpretation, the expectation of nu is equal to alpha of the Kolbach-Leibler divergence between nu and mu. Okay, these are equal by some duality. This duality has been sort of known in many forms for a while, but this paper of Singh and Vishnoi in 15 kind of really look at this and study the computational aspects of this duality. Okay. So what that is going to.
Why is it called capacity?
So I don't really know. I mean, Gurvits named it that way. I think it was supposed to have some kind of vague intuitive connection to like the capacity of a quantum channel, but I have no idea like where, you know. He's a very, he has a lot of intuitions and you just sort of, you take what he has a lot of great things to say, but sometimes you don't know where they come from. And I would say that the name of capacity is one of those things. But he also had a paper around this time that was more about quantum entanglement that also was sort of one of the spawning points of capacity. And I think maybe he had some intuition from there. But yeah, I don't know, in all honesty. Okay. So that leads into the last application I want to talk about, which is to TSP. Okay, and the problem is you're given some complete graph, let's say, with vertices V and edges E, which are everything. And you have some weights, positive, which satisfy the triangle inequality. And then you want to find a minimum weight Hamiltonian cycle. Okay, I'm going to very quickly go through just a very small piece of the history of this. I'd highly recommend Nathan's talk if you want to hear more about this. I'm not going to be able to say that much about it, but there was this algorithm, this 1.5 approximation algorithm, due to Christofides and Shirkov in around 76. Okay, it basically goes as follows. So what do? You take a minimum weight spanning tree. Let's call it T. And then with that spanning tree, you look at the vertices that have odd degree, and you find a minimum weight matching on those vertices. Okay, and then you do this kind of trick where you union these edges, and you sort of shortcut any times you duplicate, like you visit a vertex multiple times. So you can somehow take this union, do something that uses the triangle inequality to get the thing you actually want. I'll call C. Okay, and the idea is that this part, in the worst case, can be equal to the weight of the optimal Hamiltonian cycle, and this part in the worst case can be half the weight of the Hamiltonian cycle, and that's how you get 1.5. Okay, and so then much later in 2011, so this is Ovescaron, Sabiri, and Singh. They looked at this max-entropy version of this algorithm in the graphic case. Okay, but basically what they do here is they just replace this part with something a little bit different. They sample a random spanning tree T from this some maximum entropy distribution mu. And then once you sample this random spanning tree, you do the same thing here, and you do the same thing here. Okay. And the idea of this is sometimes in this original algorithm, you can maybe pick certain spanning trees that cause this matching to have very high cost. And the hope is that by adding a little bit of randomness, you can have an expectation that you're able to choose some matching or have some minimum weight matching that has cost just a little bit less than 0.5. That's the idea of the algorithm. Okay? And so with this, what we want to know, what we need to analyze, is information about the degree of vertices coming from this distribution. Okay? If we have a bunch of vertices with odd degree that have a lot of high weight edges between them, that is not something that we want because we're going to be forced to pick those edges in this matching. Okay? And so what we want to know is information like the following. How likely is it that vertices in some set S contained in V all have odd degree? Okay. And so I'm going to start off with something, recalling something that Nathan proved or discussed. I think he proved in his talk. And then I'm going to show you how we need to generalize it and exactly how we do that. So for any V in this graph, the probability that the degree of V is even in this spanning tree, this random spanning tree T, right, which is good for us, is bounded below by this quantity, which is about 0.43. Okay? I'm going to give you kind of a more sort of maybe real stable polynomials kind of way to approach the proof of this. I'm not going to say much about the proof except for just some bullet points. Okay? So you write down this the generating polynomial of this distribution mu for spanning trees. It's going to look something like this. It turns out that this is exactly one of these distributions that I wrote down before. That this is essentially just lambda to the t for some weights lambda. Okay, all max entropy distributions are of that form in some sense. Okay, and so we know that this is real stable. And then what you do is you define a univariate polynomial using some of these operations. Okay, so what I'm going to do is I'm going to take my p mu, and for all of the edges that are adjacent to V, I'm just going to plug in a single variable t. So for all the edges adjacent to V, it's going to be a bunch of different variables. I'm just going to use the same variable for t for all of those. And then for anything else, I'm just going to plug in 1. Okay, so I'm going to get some univariate polynomial, and the coefficient of t to the k is exactly the probability.
Sorry, are you singling out a specific V here, or is it for every V?
So for any specific V, we have this, and now I am, I guess, fix V in V. So I have a single V, but it can work. It's fixed, but it can be, you could have started with anyone. Yeah. Okay, so the coefficients of this univariate polynomial, the kth coefficient is the probability that in this tree, the degree of V is K. Okay? And so now there are a number of kind of results here. Nathan went through this more explicitly in his proof. But essentially, now what this means, because this was real stable, I've now used some operations that preserve this stability property to boil it down to a univariate thing. That's real rooted. And so you get that this is somehow a sum of Bernoulli's. Whenever you have a real rooted generating polynomial of some distribution, it can be thought of as the generating polynomial of some sum of Bernoulli's. This is some result from the 50s. If I'm not going to say much more than that. And then there's this bound called the Hufting bound that can be used to bound this quantity. This quantity is now a sum of the coefficients of this polynomial Q. You can think of that as representing some sum of Bernoulli's, and then there's this theorem by Hufting that gives you a bound. Note that this is not this sort of Hufting concentration bound. This is not some kind of concentration argument that you get. This function is particularly kind of weird in terms of, I would not expect it to be like you could just do something like that, like some kind of concentration bound and get something like this. This is really getting at some sum of coefficients of some more very interesting function that I don't think has any like kind of Lipschitz properties or anything like this. Okay, so this is some other bound. Like I said, Nathan spoke more about that. I'm not going to talk too much more about it now. Okay, but the idea here, the point I want to make here is that if you just care about one vertex, there are results from the 50s that can prove these types of bounds that you want to analyze this max entropy algorithm. The problem comes as soon as you want to know about multiple vertices at one time. Okay, and so for example, let's just look at two. I fixed two vertices in V. And now I'm going to try to do a very similar thing to what I did before, but this time I'm actually going to need three variables. I'm not going to be able to kind of get at the information I want with just one variable. And how am I going to define this polynomial? Well, I have two vertices that I've picked. For the edge between them, I'm just going to specify one particular variable x. And I will only plug it in for that one variable corresponding to the edge between u and v. I'm sorry, yeah.
You assume that there are no vertices of degree 1
So I am in the tree.
in the graph.
In the graph, I'm assuming that the graph is complete.
Oh,
And you have weighted edges. Yeah. I actually don't, I'm sure that if you didn't assume that, I'm sure you can, I actually don't know, but I'm assuming the graph's complete. Okay, so let's suppose I take two vertices. For the one edge between them, I set the variable x. For the other edges that are incident on u, except for this one, that's to v, I plug in the variable y. Let me do this stuff down here. For all the other edges incident to v, except for this one that goes to u, I plug in the variable z. And finally, to all other edges, I just plug in 1. Okay, so, you know, if it looked something like this, uv, this edge would correspond to x, these would correspond to y, these to z, and then all the other ones I would just plug in 1. Okay? And since I've only done these types of operations, which I told you before preserve real stability, then I know that this polynomial Q is also real stable. Okay? And I also can get at some sort of odd or some parity degree information of these two vertices as follows. So let's suppose all I wanted to do was compute the probability that u and v are both degree 2. So that's a pretty far cry from whether or not they're even degree, but at least is a lower bound. Okay? The quantity that corresponds to this in this polynomial can be given as follows. Well, if they're both degree 2, there's sort of two ways that can happen. Either this x, this edge is in the tree, and then the number of edges otherwise coming out of u and v are each 1, or this edge is not in the tree, and these other edges coming out are equal to 2 each. All right, so this is just the x, y, z coefficient of q, x, y, z, plus the y squared, z squared coefficient of this polynomial. Okay, and so then that leads to the final theorem of the talk, which gives you a way to bound these sorts of coefficients using the results that we've talked about before, plus a lot more work to both generalize it to different coefficients like this, but also more importantly, there's let me write it and then I'll tell you. So this is due to Gurvits, Nathan, and I very recently, 23. So we have some polynomial. Okay. And we have some alpha vector, which is a non-negative integer vector. If P is real stable, and if now we have this similar gradient bound, but now with respect to alpha, and also now bounded by a different constant here, then we have the following, that this particular coefficient of P that we care about, in our case, alpha would be like either 1, 1, 1 or 0, 2, 2. This is bounded below by some term. This is something that looks like the capacity bound that we use for matrix scaling. And some other term which is a generalization of this n factorial over n to the n. Actually, this part of the bound was known by Gurvits 15 years ago. Okay? And there's a couple things to say here, so I want to make just one corollary to this. What this is going to give us, how we're going to use this, is that we get a constant lower bound on the probability some constant number of vertices have even degree in T. Okay, and why am I putting constant in quotes here? Well, it doesn't seem clear how we're getting something that's constant here. So let me just give you just a little bit of points of what I mean by that. So one of the key things we needed to prove this theorem beyond the previous ones, believe it or not, was the fact that this one does not depend on the polynomial being homogeneous. This n that appears has to do with the number of variables, but not to do with the degree of the polynomial, which was kind of crucial in the previous results and turned out to be something that actually had to be overcome. So here what we now have is this n has only to do with the number of variables, which in this case, sort of essentially the number of variables is going to kind of constantly depend on the number of vertices you care about. Here it's 3. Maybe if you had 3 vertices, it would be something a little bit bigger, but also small. And the point is, so if you have some constant number of vertices you care about, the number of variables this polynomial will have will be constant. And so this n here will be some constant. Okay? The last sort of problem with this is it turns out in this whole process, you're sort of using the marginal probabilities of this random spanning tree, right? I have to say something about this gradient of p at all ones. That corresponds to the marginal probabilities of this distribution that we're talking about. And if some of those marginal probabilities end up being very close to a half, like it's sort of marginally unclear kind of whether or not the edge will show up in the tree, actually this bound degenerates to sort of nothing. You just get a 0. So somehow this has still something to do with whether or not the marginals are too far away from 0 or 1. But that is kind of the last reason why this constant is in quotes. So just want to say the last thing I'll say here is that the kind of upshot of this is a lot is known about things that are sums of Bernoullis. It's very easy to lower bound the probabilities of a number of events using this Hufting bound, which has something very general. Whereas in this case, it took a lot of effort just for us to try to bound just one of these coefficients, right? This probability that they both have even degree is much larger than just any one of these particular coefficients. Or in theory, it could be, okay? And yet the best that we can do currently, and again, after sort of a lot of work to get there, is just we can bound one of these under particular circumstances. And so I would say that there's like a lot less that's understood here. And there's a lot of, I would say, kind of not conjectures, but sort of general open problems about trying to maybe get at this directly, or maybe generalize further this constraint on this alpha related to the marginals, things like this. But in any case, this was all that I had planned to say. So thank you for listening.
Questions? Quick questions.
Yeah.
So this new theorem, is it anything about metric scaling?
So I haven't thought about it explicitly. It is a generalization of the previous result. And it at least could include potentially different marginals. This alpha would be the different like column sums of the matrix. The really new thing about this, which has to do with the fact that it no longer depends on degree, only on the number of variables. I don't know how that fits into matrix scaling, but at least I could say like for different alphas, but beyond that, I don't know actually.
Another question.
Yeah.
These distributions that you threw out, I mean, you can sample from them efficiently, or can you? Yes.
So I'm sure that was known before. There's this Singh and Vishnoi result that I stated here talks about sampling from these max entropy distributions. I can't remember if this. I would guess that this fact was known specifically for spanning trees before that you could sample from this distribution. Do you know, Nathan?
Yeah.
It was okay. So that's been known for a long time. I don't know by who, but yes. Yeah.
Questions?
What's the best known approximation ratio for the permanent deterministically?
So I think that there may be a square root of 2 to the n approximation factor that's due to Nima and Nari, and I believe I can't remember their name, one of his students, or I think, but I can't remember. I know that was conjectured by Gurvits at some point, and they solved it. But I believe that's either the best known or it's somehow is also tight below. That might be the best possible. I can't remember though. Yeah, I can try to find the paper and point to if you want. Yeah.
This capacity bound depending on this 1 minus delta to the n, and delta was the thing that you got from that sinkhorn thing. Like, does that thing in polytime can it get to this delta to be 1 over n or something to make that term constant?
You can definitely make that delta small enough to where it's going to be irrelevant to the bound. The e to the n is gonna dominate whatever it is. I can't remember exactly what happens there, but that part of the bound will become sort of irrelevant for the.
Sinkhorn converges in 1 over delta squared iterations.
Okay,
Or like polylog over delta squared iterations, that's true.
Okay.
okay,
But like it gets to a delta error, yeah.
yeah, okay, I see.
And if you use other methods, you can get like high accuracy.
Okay, thanks.
Yeah, that was just because if you care about this exact root to the end.
Yeah.
Care about that.
Well, yeah, I mean, but I guess, okay, because I don't think this root 2 to the n uses, I can't remember if they use like capacity type bounds. I can't remember the methods actually. But yeah, then it would all depend on actually how much could you improve this e to the minus n, which at least for, if you go through real stable polynomials, that e to the minus n is tight, so.
Can synchron itself get high accuracy? You do something with logarithmic.
You might be.
I thought this was the GGOW business, like this gradient descent on Riemannian manifold with strong convergence.
You might be right.
So that's how they got the better rate, no?
The way I know is that that matrix scaling is a convex optimization problem with entropy, so you can kind of do anything you want.
Right, but the question is like, what's the best rate? Is it poly 1 over delta or could you want to get
No,
poly
you
log?
can do log 1 over delta.
Okay.
In linear time by like using the max flow stuff if you really want.
I see.
Yeah. Or he doesn't.
So let's thank Jonathan again.